This is Josh White with JW Math Tutoring. In today's video, I'm going to show you how to crack the hardest digital SAT math problems with Desmos. So let's go ahead and get right to it.
But life is a dream the calculus could never predict.
Just before I begin going through these problems, I want to mention a couple things about them. First, most of these are taken from the self-reported test problem worksheets and videos that I've made previously. For every month that there's an official version of the test offered. On most of them, I have changed the numbers to make the problem slightly different. Do not have the exact same answer. I haven't done that on all of them. So just be aware, if you've done all those worksheets and all those videos for previous months, these questions most likely will look familiar to you. The first thing is just to be aware of that. Second thing is I've tried to pick problems where the Desmos solution is less work than what I would call the traditional method of solving the problem. However, there may be a couple where you are able to look at the problem and either visually or with a minimal amount of work figure out the correct answer by hand in the same amount of time or possibly less time than you solve it in Desmos. And if you can do that, that's great. That's fine. That means that you are ahead of the curve, that you are in great shape. Heading into this May test date or whatever test date you're going to be taking the test. But I'm just only going to show the Desmos solutions to all of these. I'm generally not going to show the traditional solution to them. If you want to see them, you can go back and, like I said, look at the previous month's videos for the official test questions. So with that being said, I've got Desmos window open, the College Board version of it. I've got the problems up here on the left side. There is a PDF file with the link in the description of the video and in the pinned comment below where you can download these problems and work on them yourself first, and then check your answers, check the solutions that I'm about to go over right now. So let's go ahead and start with problem number 1. So here we have a quadratic equation, and it's got some constants in it, R and S. And we want to find the largest possible ratio of R and S for there to be at least one real solution. So all we have to do for this problem is basically graph it out. And since it's already equal to 0, I'm just going to make it equal to y, and add some sliders for R and S. Now, for there to be at least one real solution, that means we need at least one x-intercept. I'm going to let s equal 1, and then I only have to adjust the r value on its slider to find what the largest ratio of r over s is to have at least one x-intercept, i.e. one solution. So if we do this, notice, okay, we still have two solutions, Now you can see the vertex coming up. And if I scroll in here, okay, notice right at 10, we have only one solution. We have one x-intercept. However, if you go anything past 10, whatever, 10.05, notice there are no real solutions. And even if you drop it down to like 10.02, 10.01, again, there's no real solutions here. Okay, this vertex has a y value which is greater than 0. Therefore, there are no real solutions. There are no x-intercepts. So the correct answer for this problem that you can see right here is just going to be 10, because r over s right here, what's the largest ratio I can make such that there's one real solution? It's just 10. So correct answer for number 1 is just 10. And let's move on to the next question. All right, question number 2. Here we have two rational expressions that are being basically added, at least on the right side, and they give you what the final answer is on the left side, but they want to know what you start with on the right side, or specifically what the constants have to be, for p and w. So we can just very easily do this with regression, where I just take the left side, and then I do a regression statement, and I set it equal to the right side. Now, Just expand that so we can see the whole thing. Of course, I have to make a list for x1. So you do have to be careful here. Notice 3 is not an acceptable value for x, because if you plug in 3, you would get 0 in the denominator. So you do have to be careful that as you're making your list, you cannot use 3. You have to use some other number. So now notice, and I just put in some other numbers here, 1, 2, 4, 5, 6. I've got a value for p. I've got a value for w. It does not say that they need to be integers. It's not given in the problem, not required in the problem. So now what are the values for p plus w? It's just 13. Also doesn't say they have to be positive either. We're basically given this example problem, we're given no information about basically essentially they are non-zero, but the regression automatically handles that. It doesn't need to be stated. So p plus w is 13. You can match up again the final this final answer to its like two rational expressions it was formed by adding, or you could also do it with subtracting or multiplying or whatever. And so we know that p plus w has to equal 13. Next up, let's look at an exponential function that deals with percentages. Question number 3. So we have an exponential function which is equal to some constant times some number b to the raised to the x power. So I am going to just set it up like this. For my a constant out front, I just chose 1.5. For my b value, I chose 2. Okay, so now what's happening? When x increases by 1, the function increases, f of x, meaning the y, increases by c%. Find c in terms of b. Okay, so first we have to find the percentage increase for a 1 unit increase in the x value. So for example, percentage increase is just the new value, which I'm going to make f of 2, minus the old original value, which is f of 1, and then divided by the old or original value, which would be f of 1. Now this is the number, but to convert to a percentage, of course, we have to multiply by 100. So it looks like when there's a 1 unit increase in the x value, the function increases by 100%. Okay? So now, let's just go ahead and make this 4, make this 3, and make this 3. Notice we still get the same answer. So the x values I pick to look at the 1 unit increase do not change the overall answer that I get. Okay? So the point is, c is equal to 100. That's the percent that the function, the y value increases by, when the x value increases by 1. Now, it says find c in terms of b. So all you're going to do is go through these answer choices, and we're going to say, okay, we're looking for the 1 that's equal to 100. And you could probably do this just by looking at it. Okay, so obviously it's not a. It is going to be b. 100 times b minus 1. You could also check C, nope, and you could check D, nope, those are incorrect. So the correct answer for this one is going to be letter B. Now, I just want to show you, if I pick different values for A and for B, I should still get the same answer. So let's say for B, I pick a number now, which is 1.4, and let's say for A I make this whatever 0.5. Now notice my percentage change for the function with a 1 unit increase in x is now only 40%. Okay, so I have 40 here for the percent change, percent increase really calculation, and therefore the c I'm looking for is 40. So now I go through the answer choices and I plug in, plug in the b value that I chose, which is 1.4. And again, b is going to be the only one that gives you 40. Okay, so the specific a and b values don't matter. Now the key in this problem is technically b does have to be greater than 1, because otherwise the function would not be increasing, it would be decreasing. So it has to be a positive number, obviously, and it has to be greater than 1. So I don't know if that was defined in the problem. I'm not sure. But based on the description, the fact that it's increasing that basically tells you that the b value has to be greater than 1. Okay? But the specific a and b values don't matter. You still get the exact same answer, which is letter B. All right, let's look at another percentage question now. This is number 4. So we have three numbers, A, B, and C, constants, and there are various relationships between them, and P% of B is C, and we want to know what's the value of P over 1,000, and so on and so forth. Okay, so first thing I would do here is I would start by defining B equal to 100. Then I would note that A is equal to 628% of B. Notice that tells us that A is going to be equal to 628 based on the value of B that I chose. Now I'm going to do a regression statement with A and C because that will take the value of A and that will allow me to find the value of C. So notice I can actually just type it like this. I can just type 0.32%. I don't even need to convert it to a decimal. Okay? Now I have a value of C. So now what I need to do is basically find the value of P and then take that P value and take that once I find it and just divide it by 1,000. So the thing is, what we can do is we can actually now just type the equation relating B and C and P. In other words, and I'm going to just type the C part on the left, even though it's second. C is, is C is just equals C. So I'm just going to do C equals P% of B. Because I chose B being 100, notice that P is actually the same value that I get for C in the regression. And in the regression, notice it actually changed up here to the value of P. That's fine. That doesn't matter. I'm just taking this equation right here, and I'm just typing the thing straight into Desmos. So now I have P. So what is P divided by 1,000? Okay, it's 196.25. So for this problem, technically there would be two correct answers. You could put 196.2 if you truncated the decimal, or you could put 196.3 if you rounded the decimal. Now, if you convert it to a fraction, you get 785 over 4, so it looks like we could enter that in as well. Because, yeah, that would only take up 5 total spaces, 7, 8, 5, the division sign, and 4. So any of these three answers would technically be acceptable for this problem. Now, an alternate way that you could have gotten the value of P is you could have now taken the equation and typed it like this using x. You'd have done x% of B equals C. And then you would look for the vertical line for the value of P. The problem is it's such a gigantic number, you have to keep zooming out, zooming out, zooming out. Where's the vertical line? Okay, here it is. It's right here. So then you go over here, and then you take this value, whoops, and then, of course, divide it by 1,000. And there's your correct answer. So that's just an alternate way to get the value for P, just by basically typing the equation but putting an x in and then looking for the vertical line which solves it. Now let's go ahead and take a look at the next problem, number 5. So here we have an exponential function, and you're told some information about it, basically how f of n and f of n minus 1 are related. It asks to find what the value of b is in this exponential function. So the really cool thing is that when I come across this problem previously, I did not know of a way to do it really easily in Desmos. However, I have now figured out how you can do that. And what we're going to do is basically set up a regression where we match some of the f values with what they're equal to in terms of that statement there. So here's what I mean. First step, I'm just going to type the generic function, okay, that looks like this. All right, now what I'm going to do is I'm going to type a list. Okay, and in this list, I am going to put f of 0, f of 1, f of 2. Okay? And then what I'm going to do is I'm going to regress that to what those values are actually equal to based on the formula. So the thing is, it does require just a little bit of work here in recognizing that if you're solving this, to solve this formula for f of n, you would subtract this over to the other side. So in other words, f of n would be equal to f of n minus 1 minus 0.86 f of n minus 1. Okay? So what I'm going to do now is we're going to note that, first of all, I'm just going to set f of 0 equal to 1, just, kind of as like a starting value. Say like this function goes through 0, 1. All right? So in other words, I'm saying I'm starting off with 1 point for this function as 0, 1. Okay. Then I know that f of 1 is just equal to f of 0 minus 0.86 times f of 0. And then I know that f of 2 is going to be equal to f of 1 minus 0.86 times f of 1. Okay. All right, now it's not giving me an answer, but looking at what I typed in, there's an extra bracket here, which I believe will be the problem. So let me get rid of this. And there's also, let's see, an extra parentheses. So this should be closed off here. And one, don't need this. Okay. There were just extra parentheses, extra brackets that were causing, basically, that were causing the issue, causing the regression not to work. Okay. So now let's just check. Yeah, everything should be fine. All the parentheses should be matched up. And notice it works perfectly. It gives me value for A, it gives me value for B, so there's my answer, just 0.14. All right, now, and just to show you, let's say in this problem, instead of, whatever, 0.86, let's say the number was, I don't know, 0.43. So now all you'd have to do is basically just go through, change this to 4.3, change this to 4.3, and okay, and same thing that works, gives you your answer for B. There. So this is basically showing you how you can regress x values to y values, and specifically do them in terms of f of something, f of a value, f of 0, f of 1, and you can define them in terms of each other. So that's what's kind of special or unique about what I'm doing here. Like, I'm telling it that f of 0 is 1, so I have the point 0, 1, right? But then everything else is kind of built off that. Everything else is calculated, the next point's calculated off f of 0. And then the next point, and that's f of 1, the next point then is calculated off f of 1, and so on and so forth. So this is a new thing, really, that I just discovered when looking at this problem, and it'd be useful for an exponential function, potentially like this. All right, let's look next at number 6. So this problem you've probably seen multiple times before if you have watched my review worksheets. So a couple things. There are actually multiple methods you could use for this. The way that I like to do it is to just type the whole thing in, and then just do a regression to get A, B, and C. And then just add them together. So 4 squared, make this an x1. Okay, so we're regressing. We're taking this equation, just make it into a regression statement. And now we, of course, have to add the list for x1. Okay, now we've got enough values. It looks like everything has stabilized, and we can do A plus B plus C. So what's our answer? Well, it's 48, and that's it. Okay, now I will show you an alternate method that you could use to solve this in Desmos, which is basically, so let me just delete all this. If you notice, if you plug in 1 for x, the left side here will just turn into a plus b plus c all over 4. So that means if you evaluate the right side for 1, in other words, type in our function from the right side. Okay, so now f of 1 equals that. Now, what did I mistype? Oh, it's not giving me here. Sorry, there we go. There's the correct value for f of 1. All right, so this is equal to a plus b plus c times 4. So now a plus b plus c is just 4 times this. So correct answer is 48. This is an alternate way you could do it if you recognize that plugging in 1 for x makes a plus b plus c over 4 on the left side, or in other words, a plus b plus c is equal to 4 times the function evaluated at 1. Okay, so that's just an alternate method you could use in Desmos. All right, let's look at question number 7 next. So this is actually something new. It was in my part 9 video. Basically, what we're going to do is we are going to do regression again. But what we're going to do is we are going to regress the given equation, basically the left side of it really, with essentially its factored form or its intercept form. So I'm just going to put 3 parentheses here. A, B, and C represent the 3 roots or the 3 x-intercepts, 3 solutions to this problem. Okay, so now that we have that, then we have to set up the kind of like the constraint equation, or in this case it's the product of roots equation, which basically says, okay, ABC is equal to 56, because A and B and C, as I define them here, are my 3 roots. Okay, the 3 letters inside the parentheses. However, it doesn't work unless we define this explicitly for one letter. So I'm going to define it for A and make it equal to 56 over BC. All right, now I'm almost done. I need to do my list for x1 to tell the function, or the regression, excuse me, to treat x1 as a constant. I'm going to start with -2, 0, and 2. And once I've entered enough values, notice I am getting what is the correct answer for k, which is 17. Okay, so that is how we could solve this entire problem in Desmos using regression. And if you want more information about this, definitely check out Part 9 in my Ultimate Desmos Guide to Digital SAT Math. There are more examples that go through this. All right, next up, let's take a look at question number 8 here. Here you have an equation with a square root, and it has one real solution. So what we're going to do for this one is we are actually going to square both sides. Okay, so, and you could write the squareds in here, it doesn't matter, but when you square, for example, the left side, you're just going to become k minus x, and then on the right side, you can just leave it as 9 minus x squared. And the reason I'm going to do that is because, first of all, this is how you would typically solve it, but now it's turned it into a quadratic, okay? Since the quadratic has one real solution, I'm going to regress this equation, which I'm going to manipulate in 1 second, to its vertex form, and I'm going to let the k value in its vertex form be 0, because one real solution means that the quadratic function, the parabola, whatever you want to think of, has its vertex on the x-axis, which means its y-coordinate of the vertex is 0. So here is exactly what I mean. I have k minus x, okay? Then I'm going to subtract over the 9 minus, and I should make that x1 actually, the 9 minus x quantity squared term. So now it's equal to 0, all right? Then I'm going to again regress this to its vertex form. And again, Normally, you would see like plus k at the end here, but again, k is 0 because there's only one real solution, which means the vertex is on the x-axis, which means the y-coordinate of the vertex is 0. All right, so now I can go ahead and I can enter in my values for x1. And you see after I enter a couple, okay, notice it's finalizing, in here on the correct values. So notice for k, it gives me 8.75. However, this question is not asking for k, it is asking for 4k. So what is the value of 4k? It is 35, and that's it. Okay, so that is how you can solve this problem entirely in Desmos by using regression, basically between two different forms of a quadratic function, and then just making your list for x1. All right, next up, let's look at problem number 9. So here you have a polynomial, technically third degree, cubic polynomial. And you're given some information about it, and then you're asked to determine which of these, 3 statements could be true. So the easiest way that I think to do this one is to just pick some numbers for a, b, and c and basically visualize this. So what I'm going to do is I'm going to type in the function and then add sliders for all these values. And I made a 2, I made b 5, and I made c 8. And let me just slide this over and zoom out. Okay, so we can get a better picture of the graph and what's going on here. All right, so first of all, notice, are my conditions being met? When x is between a and b, so when x is between 2 and 5, looks like, yeah, here's 2 and here's 5. Is my f of x positive? Okay, the answer is yes, it is. Okay, so that works. Now, the next thing is we have some point with a y-coordinate of 6. So what I'm going to do is I'm just going to graph y equals 6. There are 3 different points here on the graph which have a y-coordinate of 6. Here's the first one, here's the second one, here's the third one. Okay? We can export each of these if we want. Now, if s equals 6, which of the following could be true? All right. So, is it possible that r is less than a? So, a is 2. Are any of these x coordinates less than 2? No, they are not. You would eliminate it. Is it possible r is between b and c? Okay, so b is 5, c is 8. Are any of these r values between 5 and 8? No, they are not. This one's greater than 8. These two are both less than 5. All right, so it looks like it's going to be number 3 only, basically by process of elimination, and that is the correct answer, letter C. But let's just confirm it. R is greater than C. Okay, I chose 8 for C. Do I have an R value somewhere here that is greater than 8? And the answer is yes, I do. This point right here has an R value of 8.15, blah, 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 whatever. That is more than 8, which is more than C. Therefore, the only possible correct answer for this one is letter C, 3 only. Okay, and again, this is how you can do the entire thing in Desmos just by picking some numbers and graphing out the function and getting a visual idea of what's going on here. All right, next, let's look at number 10, solving a formula for a specific letter. So the method that I like to take on these is I type in the entire equation, except I am going to replace the letter that I'm solving for with y. All right, so I replaced q with y because we're solving the equation for q. Now, I just need to add some sliders for p, r, and s. So I'm just going to move p to whatever, 2.8, r to 2.5, s to whatever, 3. All right, so now I have a nice horizontal line here. Okay, so all we have to do is just type the answer choices. They're going to be horizontal lines as well, and we see which one completely overlaps the original line. So answer choice A clearly does not overlap it, so that is not correct. Let's look at answer choice B. P plus R plus S. Does that overlap it? Nope, not correct. Let's look at C. Let's divide this. This is not overlapping it. I mean, it's pretty close, but again, it's still not directly overlapping it. So it looks like it's going to be D, but let's just graph it out to confirm. All right, and notice, oh, there we go. Now look, it is completely overlapping the original graph. That confirms D is equivalent to the original given form of this equation, and D is the correct answer. Okay, and again, that's how we can solve a formula for a single letter entirely in Desmos. All right, next up, question number 11. Here we have another sum of roots problem. And so what I'm going to do on this one is, again, first get this everything equal to 0 in this equation, and then regress it with its intercept or factored form. Okay, so that means I've got this left side. I have to subtract over the entire right side. Okay, then I'm going to enter a regression statement. I'm just going to use m here as a constant out front because a is already taken up. And now I have, notice this is a quadratic. We have x squareds. We don't have any powers above that. I can't use a since that's already chosen, so I'm just going to use b and c as my two roots. Now we also know the sum of these roots, so in other words, b plus c equals 2k plus 29. But again, this equation, this part, it has to be in terms of only one letter equals everything else on the other side. So I'm going to do b equals this, 2k plus 29 minus c. Now I can do my list for x1. Start with negative 2, 0, and 2. Okay, so now when I go through this, what is the value of a? And notice this gives me the answer of negative 7. So therefore, that's the correct answer. Now, I want to point out, I think the text on this problem might have been wrong. I think this was originally intended to ask for k, not for a. Or actually, no, the k's will cancel out. It is intended to ask for a. So, all right, never mind. Ignore that. Correct answer, negative 7. This is how we can solve the problem. Again, entirely in Desmos by using regression for a sum of roots question and get our answer. Okay, let's take a look now at the question below it. Number 12, another percent problem. So first thing I'm going to do here is I'm going to do A is 20% of C, and then I'm going to do C is equal to 20% of B, and I'm going to start off now by defining B as equal to 100. Okay, so doing that calculates both the values of A and B. All right, so I defined B as 100. I got a value for A, got a value for C. Okay, so now it tells me that A minus B is equal to W times C. So what is the value of W going to be? Well, A minus B, and I can just do a regression statement, is W times C. Right there is my answer. It's 23. That's it. Don't need to do any more work, than that. You can just type in basically the two percentage equations. You pick a number for B. Then you take this equation, you turn it into a regression statement. It feeds in A and B and C. It solves it for W. That's your answer, 23 right there. Nothing else to do. All right, let's look next at number 13. This one was function with some absolute value expressions in it, and telling you that A and B are greater than a number, and f of 432 is h, and f of negative 418 is k, and so on and so forth. Okay, and they want to know what's the value of this expression, blah, blah. All right. So we can actually do this fairly easily in Desmos. All we have to do is first start off with the original function itself. Plus b. Okay, now we can add some sliders for a and for b. So we know that b is greater than 65. They do not have to be integers, but whatever. I'm just going to choose 66, and a is greater than b. I'm just going to make it 68. Okay. All right. So now that I've got those selected, I can find f of 432, some gigantic number, and I'm going to let this equal h. And then I can find k, which is f of negative 418. Notice they specifically chose these two values such that they both have the same y value. In other words, they're symmetric, essentially. So now, what's the value of 4 times 432 to the h minus, you gotta be careful. For some reason with exponents, it's a pain to type in when you want to add or subtract something, and then plus 3 times negative 418 to the h minus k, and there is our answer. The answer is positive 7. And we can do the entire thing in Desmos, and you probably already recognize the reason that this happens is because since h and k are the same, like these two x values have the same y value, basically they're symmetric points, what ends up happening is, this h minus k is 0, so this whole thing goes something to the 0 is just 1, and the same thing happens in the second expression, so you really just end up with 4 plus 3 equaling 7. But anyways, this is how we could do the entire thing in Desmos just to calculate it for us and confirm it. All right, next up, the next question, number 14. Here we have a quadratic equation with a constant in it, and we have one of the solutions to this quadratic equation, and they want to know the value of c. Okay, so again, this is a new thing that was covered in my Ultimate Desmos Guide to Digital SAT Math, Part 9. And all we have to do is there's actually two ways to do it. I don't know if I'll show both. We can basically take this thing and do a regression statement. And then what we have to do is basically we're just going to define what w is equal to, which is this, negative 9 plus root 497 all over 16. And so now that we have that, we have the correct answer, which is negative 13. So c is negative 13, and that's it. This is how you can solve this problem completely in Desmos. If you want to see the second alternate method, again, go watch my video, Part 9, Ultimate Desmos Guide to Digital SAT Math, and look at this type of problem. It's this type of Desmos operation. It's the first one in the video, and you can see the second way you can also enter it as well. All right, let's now look at number 15. We have an equation for a circle. It is not in standard form. And we want to know what the value of t has to be in order for this circle to have a radius of square root 62. Okay, so we're going to use regression with the equation we're given and the standard form of a circle. However, there is one thing that you do need to be aware of when doing this. So standard form equation of a circle, x minus h squared plus y minus k squared equals r squared, right? I'll just write it here, just so we have it. Notice, there's a 1 in front of both these parentheses. However, this given equation does not have a 1 in front of the x squared or y squared terms. That means in order to do this regression, you have to divide every term by 2. Now, if you want to put a 1/2 out front, that's fine. That will work, rather than manually dividing every term by 2. So if you just want to do a 1/2 like this, and then you can do, x1 squared plus y1 squared. Oh, actually, sorry. Then we would just type the original thing that you're given, plus tx1 plus ty1 minus 60. Okay, we are going to regress this to its standard form, which would be x1 minus h squared plus y1 minus k squared. And then normally it's equal to r squared, but again, we have to get this equal to 0 in order to do the regression, so I'm going to subtract this over, so it's going to be minus r squared. Except we know that the radius is root 62. That means that r squared is equal to just 62. So I can just type in here 62. All right, so now I have to define lists for x1 and y1 because I wanted to treat them both as variables. So let's put some points in here for x1. Let's put in some similar points for y1. Okay, and now we have everything, let's see, working out nicely. We get t equals negative 16. Is that the correct answer? I thought it was supposed to be, I had down in my notes here positive 16, but let's see. So we have negative 16, so let me just jot that down. Let's try getting, let's see if the 1/2 is what is messing with things, and instead do the divide everything by 2 method. Or 2, it's 30. Okay. And we get the exact same answer. So looks like, yes, the correct answer for this should be negative 16. Okay, so just want to mention one more thing after thinking about this and checking on something. Negative 16 is a correct answer, but there's also an additional correct answer of positive 16. If you do this out by hand, and actually do out the algebra, you'll see that basically t can either equal positive 16 or negative 16. It doesn't matter in terms of where the center is. You would still get the same radius. So negative 16 is an answer, but you could, let me just see here just to confirm. If I put in a qualifier, makes t greater than 0. Yeah, you can see here we get the same value for t. It's the same h and same k, but the t value is now being positive. So negative 16 is correct, positive 16 is correct. Either one, it doesn't matter. They're both correct answers. All right, let's look next at number 16. So here we have, again, this is something new. This was discussed in my Ultimate Desmos Guide to Digital SAT Math Part 9. We have a system of equations. It has constants in it. We are trying to find the value of one of those constants such that the system has infinitely many solutions. What we need to do is we need to get all of the x and y terms on the same side for both equations. So that means, let's say, move this over to the left and move this over to the left. And then we're just going to do a basic regression of the x constants from one equation on top of the other and set that equal to the, not regress it to the y constants. All right, so the top equation, the x constants we have on the left side are coefficients, 1/2 minus 3/4, okay? You don't have to bother combining them. Desmos will do that for you. On the bottom, there's only one x coefficient, and let me just erase this so we can see it, and it is 2/9. Okay, so this right now is x coefficients on top divided by x coefficients on bottom. Now for the y coefficients on top, we have the 9/2 plus 5/2, and on bottom we have just h, and that's it. So here, now we have our answer right here. Negative 6.222222, so you could enter this as negative 6.222. Obviously, rounding and truncating is the same. Or you could enter this as negative 56/9. And again, that is how you can solve this problem entirely in Desmos. You do not need to do, you need to do a little work, you can do it visually or you could write it, but getting the x and y terms all on the same side. But the point is you don't need to bother like multiplying these out and getting them into both slope-intercept form and then setting the slopes equal to each other, or looking at like the x multiplier and the y multiplier and doing all that stuff by hand. You can just do this entirely in Desmos. All right, now let's take a look at problem number 17 at the top of the next page. So this problem actually has two different methods you can use to solve it in Desmos. Of course, I'm going to demonstrate both of them. So the first method is to use regression. And there's actually two different ways that you can get it to work by doing that. So one method is just going to be typing, put an x1 here, the original equation out, okay, and then we're going to regress that to the expressions that we see on the side. Should be 2x1 squared plus b. Okay. Now, of course, we need to add a list for x1. All right, so we have some a and b values there, right? Okay. Now, if you want to do it for c and d, what I'm going to do is I'm just going to copy this, but I'm going to change it to 2 instead of 1. And then now I'm going to change these letters to C and D. And of course, for that one, I now need to do a list for x2. I'll just put in the same things, 1, 2, 3, 4. Okay. But notice it's giving me the same values, right? It's giving me 13, 5. So how do I prevent it from doing that? How do I force it to give me the non-integer values? Well, the easy way is just put in a condition here. And let's say I'm going to make C less than 10. Notice when I do that, it now gives me the other set of solutions to this, which are the non-integers. Okay, so now you could just go, what's a plus c? Well, 20.5, or if you want to do it as a fraction, 41 over 2. All right, so that's our first method to solve this, and there's our answer. Okay, so first, you probably saw the video froze there at the end of this first solution method. But anyways, we get 20.5. So now I've retyped this all in. I don't know why it's not giving me the option for the decimal here, or the fraction, adding a plus c, but it's 41 over 2 that you could type as, enter as an answer as well. Okay, so again, what I did here is I did regression, I did it 2 times, and I put in a qualifier to basically force it to not find the same answer the second time. And you could do the same thing. You could put the qualifier on D, and you could say, like, D is greater than 7. All right, and then it returns the same values, the 7.5 and the 8.666, repeating. Okay, so this is one method using regression. An alternate method using regression would be as follows. You can type, I just noticed here, when I retyped this, I typed x1. Technically, I typed x2 when I did it in the first part of the video, so sorry. This really should have been x2 here, but as you see, it doesn't matter, doesn't change anything. Okay, so now, let me just, yeah, it's still not getting the fraction thing. Okay, here's an alternate approach you could take. So, I'm going to get rid of this. Okay, I am going to get rid of this. I'm going to change this back to x1. I'll explain why in a second. Okay, so notice here I have two statements. It's giving me the same exact answers, but that's not what we want. We want the integer answers and we want the non-integer answers. So one way around this is you basically switch the order of the parentheses. Okay, so you do two different regressions. So let me get rid of this. Notice, I don't know why it works this way. I have kept everything x1. Okay, so I have x1 in my first regression, I have x1 in my second regression. Then you switch the order of the parentheses. So in the first one, you put the 3x1 squared first. In the second one, you put the 2x squared parentheses second. Make sure you keep the corresponding letters, the A and the B and the C and D with the right numbers, okay? But if you switch the parentheses, I don't know why, it'll automatically force the second regression statement to give you the other possible solutions, which in this case are the 7.5, comma, 8.66667. And then you could just add again a plus c and get 20.5. All right, so this is a second method you could use involving regression to solve this. Now, here is, technically, I guess this could be the third overall method, but it's really the second different method. The way that I like, honestly, to solve this problem as well is to notice it's really going to be a system of equations. So what I mean by that is, if you FOIL these expressions out, right, basically, when you do that, we already know that 3x squared and 2x squared is 6x to the fourth. Okay, so that we don't care about. And we already, but we do know that a times b, is going to be 65. And same thing, c times d, is also going to be 65. And we also know that when we do the inner and outer terms, we need them to equal 41. In other words, we need the inner 2a plus the outer 3b to end up equaling 41 for the x squared term. And the same thing is going to be true with c and d. It's going to be 2c plus 2d equals, 2c plus 3d equals 41. Okay, so now what we can do is we can just go into Desmos, put in a basically we're going to solve a system of equations using regression. So we type the left side from both top and bottom. I'm just doing the A and the B thing first. And then we type the right side, which is 65 with the top and 41 with the bottom. Okay, so there's my first answer. So now what I'm going to do, I'm going to do the same thing again. I am going to use now C and D instead of A and B. But again, it's giving me the same answer, right? I don't want the same answer. I want the other answer. I want the non-integer values for C and D. So here again is where you would put in a qualifier. So something like C is less than, let's try 12. Okay, perfect. And notice now I have my answers. I can go A plus C. Here it does let me click on the fraction thing. Okay, 41 over 2 or 20.5, which is the correct answer to this problem. So first, let me just mark that down before I forget. Okay. And also, again, you could do it on D as well. So like in the original one, the B, or think of it as the Y, second letter, is 5. So let's do D is greater than 6. Okay, perfect. It works. It gives us the non-integer values by putting in that condition. So again, this is another way that you could solve this problem as well. All right, now let's take a look at number 18, right below it. So here we have, let me just clear out Desmos first. Oh, too far. All right, here we have a quadratic expression, and we want to know, we're told that r is positive, s is negative, and we're told that r over s is greater than k. Find the smallest possible value of k where the equation has two real solutions. All right, so first thing I'm going to do is I'm going to type in this entire thing. Okay. Now, I'm going to add sliders for r and sliders for s. Since s is negative, I'm just going to make it -1. And now I'm also going to do r over s, since that's essentially my k. It's not your actual k value. It is the value that is greater. We want to get this as small as possible, but still see two real solutions. So since I've already made the s negative, that means I'm going to increase the r value, because notice r over s is getting basically it's getting larger from a negative perspective, meaning it's getting smaller. So I just have to move this. Actually, okay, so I can move this, and notice when I get to 4, it actually jumps right here. So notice when r is 4, r over s is -4. Okay, so notice now I've found a value such that there is one real solution, but we want basically we want this k value to be as small as possible, where it actually has two real solutions. So the thing that's a little tricky about this one is K is like your floor or your lower limit, and we need the R over S value to be greater than that. It's not greater than or equal to, it's strictly greater than it. So it's like if I change this to, 4.01, okay, or actually no, I want to go, sorry, I want to go the opposite way, 3.99. Notice, and I can add, like, even I add another 9 there. Okay, notice there are two real solutions right here. There are two x-intercepts. So negative 3.99999, that is the smallest possible value that I can get for, the R over S ratio, which just confirms that my smallest possible value for K, which is the floor, is going to be negative 4. I mean, basically, negative 4 is the answer for K because there's one real solution, okay? Meaning that if you make the number any larger than negative 4, then there's going to be two real solutions. So in this problem, the K value is basically it's basically the value such that when I move these sliders, I get exactly one real solution because I'm looking for the smallest possible value such that there are two real solutions. So the value that gives me one real solution, like that's your floor, that's your answer. All right, next up, number 19. Let's look at another problem here that deals with circle regression. So what I'm going to do first is I am going to notice that the circumference of this circle, which is 4 pi root a, I am going to I'm going to set that equal to r, with remembering that circumference is equal to 2 pi r. So therefore the radius, if you solve for it, would be equal to some circumference divided by 2 pi. So first thing I'm just going to type in is the circumference, which is 4 pi square root a, and then divide that whole thing by 2 pi. All right. So I've set r equal to that. Don't worry about, whatever it shows on the screen. Then I'm going to go ahead and do my regression. With x1 and y1. Notice this one's already set equal to 0, so that's fine. And then I'm going to regress it to basically standard form. Okay, so now got to do my x1 list, and I've got to do my y1 list. Okay, so notice this has gone ahead and given me everything that I need. Basically, it's given me h and it's given me k, and you can check these are correct values if you go ahead and complete the square and everything and work it out. And more importantly, it's found the value of a for me because it does this regression, setting this given form of the equation of the circle equal to this standard form equation, and it finds what r has to be, and then it takes that and it goes back to this equation where I defined r, and it says, okay, well, if r is this, what does the value of a have to be? And the answer is just 45. And you can see it, right here. So this is how you could do circle regression to not only just solve for the radius, but if you have some expression for like the circumference or the area which has a constant in it, to solve for that as well. All right, so next let's look at the question underneath it, number 20. All right, so in this problem we have an exponential function. The one thing to be aware of, though, is that this m represents a number of minutes, whereas this question is asking about a p% increase in every 180 seconds. So they're not the same units. All right, and they want to know which of these expressions is equal to p, this percentage by which it's increasing. All right, so we can solve this entire problem in Desmos. First thing I would just note is that, 180 seconds, just divide that by 60 seconds per 1 minute, that's going to be equal to 3 minutes. Okay, so the m value that I'm going to use is going to be 3. So it's talking about this increasing by p%. So I'm going to look at the percentage increase formula. Basically percentage increase formula says we find, and first I'm going to define it, the function here. I'm going to use x instead of m. Now, for q, I'm just going to pick, whatever random number. I think when I did this initially, I chose 2.2. And then the percentage increase formula says, okay, so every 180 seconds or every 3 minutes, there's this p% increase. So I'm going to compare the values at 3 minutes versus the values after 0 minutes. So n of 3 minus n of 0. So it's like the new value minus the old value divided by the old or the original value. That is the formula for, basically it's the formula for percent change, which in this case it's an increase, but you could just use it for decrease as well. Okay, so notice this is the decimal equivalent, so if we want the actual percentage, we're just going to multiply it by 100. So now all we have to do is we just have to go to the answer choices and see which of these formulas corresponds to an 80.64% increase. So the first one obviously is wrong, gigantic number. Okay, let's look at B. Notice here we have the exact same number on the screen that we're looking for. So this is going to be the correct answer. Now, if you wanted to try out C and D, so notice I'm going to try D first, just to show you that because you just changed this to a plus. Okay, obviously that's wrong. That is not correct. And now if we want to go back and try C, get rid of this 3/4, make it a 3. Okay, that's obviously not correct either. So this just confirms the correct answer is B, and this is how you could do this entire problem in Desmos. All right, next up, on the last page, let's look at problem number 21 here. So here you have a function, and all we really have to do for this one is just take z, replace it with negative 43, type in the 16r squared minus 600. Okay. Now, since negative 43 is a solution, that means when we plug it in, we should expect to get 0. So all we have to do is regress this to 0 and just get our value for r. And let me just confirm here. I get r equals 6.25. Now, you could, of course, express that as a fraction. It would be 25 over 4. The other thing about this question is that technically there is a second answer, and it's just negative 6.25. Let's see if it can find it if I put in a qualifier to make r less than 0. Yes, it does here. So positive 6.25 is an answer. Positive 25/4 is an answer. Negative 6.25 is also an answer. Negative 25 over 4, also an answer. So there's 4 different answers you could write in here. All are correct. And again, this is how you can do this entire problem entirely in Desmos. All right, next one. Let's talk a little bit about doing linear regression, but with lists instead of a table. So here you are given 3 points. Notice 2 of the points have a constant k in it, which they don't tell us what it is. We want to find the equation of this line. So all we're going to do is we're going to define the first point's x values in a list. And we are not going to add a slider for k. We don't need to do that. Then we're going to do the same with, whoops, forgot to start the brackets. So let's put that here. The y1 values. Now we just have to do basic linear regression. and there's our equation. There's our slope, there's our y-intercept of 0.8 or 4 over 5, slope 5.2, or that should be 26 over 5. Yep, 26 fifths. And then they also give you the k value here. Now, in this case, we're not it's negative 14 over 13. We're not asking for the k value, but just if it was asking you for the k value, um, this is, you could get that as well, and that's it. So that's how you can do this problem. Just write it out here. Y equals 5.2x plus 0.8. Again, that's the decimals, fractions 26 over 5 and 4 fifths. All right, next up, question number 23. Here we have a quadratic equation with a constant, and we're given a solution to it, and I want to know what is the value of that constant. So again, very simple question to do in Desmos. All we have to do is type in a regression statement with the c, set it equal to 9, and then we can go ahead and set x1 equal to the solution that we are given. So just type that whole thing in. Notice it now gives me the correct answer of positive 8. So c has to equal 8, and that's it. Again, we can do this entire thing in Desmos, in a matter of seconds. All right, let's look at this problem now. We can go ahead, question 24. You have a rational expression, you have some points. We're trying to find the other point where the graph of this is equal to 0. So we can just go ahead, we can make a table, we can enter the 2 points, then we can go ahead and we can do regression for this. So y1, and now on the top, on the bottom, we just put in the all right. What is the error it's given me here? X1. Oh, I forgot to put the x1. There we go. Perfect. All right. So what's the value of q? Where is the other point where this is equal to 0? So it's a little tricky to see, possibly on the graph here. Like, you have to kind of click around on it. But 11, this point is given right here, 11, 0. What's the other point that has a y value of 0, i.e. v of q equals 0? Well, it's right here. It's 8, 0. So the correct answer for this is just going to be 8 for your value of q. Now, an alternate way you could do this as well is if you just get rid of the denominator, because really in a rational function, when you're looking at setting equal to 0, all you care about is the numerator, right? Just basically, if the whole function is going to equal 0, that means the numerator equals 0. As long as the denominator is not 0, then we're only concerned with the numerator. So if I do that, if instead you want to just do it like this, then, let's see, no, that's not what we want to do. What I want to do is, sorry, not that. Let me go back to my original graph. Okay, sorry, here's what I meant to do. Instead, you just want to graph the numerator itself. Once we've already found b and c, we can get rid of this, and now it's easy. Sorry, now it's much easier to see the other x-intercept at 8, 0. Okay, so again, all I did is I entered the points, I did the regression, and now I went ahead and basically found what the other what the other intercept is just by looking at the other x-intercept on the graph. All right, last problem on here, number 25. Let's talk about this question. So What we're going to do to solve this one in Desmos is we are going to do regression, where we set this expression, and we're going to have to get it, the whole thing equal to 0. So I'm going to have to move the minus px over to the left by adding it, and the w over to the left by subtracting it. All right, then, again, we're going to use regression, and we are going to regress this to its intercept or factored form. And the two intercepts are, basically two solutions, really, are w over 2 and minus w over 2. So that means one parenthesis is going to be x1 minus w over 2. The other one is going to be x1 plus w over 2. Okay. I can't quite do this yet, because we need to have a list here for x1. So I need to go ahead and just define some values here. 2, 0, 2, 3. Okay. There we go. We got enough values, and notice it's given me the value for p of negative 12, which is actually correct, because if you're going to have two solutions that are opposite values, that means it's technically factorable as a difference of squares, which means all the x terms cancel out. So that's why the p is negative 112, but in any case, don't worry about that. So it gives me a value of w. So one potential answer for this is w equals 2. All right, so we get it right here. There is also a second potential answer, so in order to do that, we're going to have to put in a condition. So let's try going down, w less than 1. Okay, so we do actually get the second correct answer here of negative 3.3333. It's basically, you could do negative 3.333, or you could also do its equivalent fraction form, negative 10/3, if you wanted to enter it in that way. Now, just a piece of advice. Let's say you try to go the other way, okay? So like our original answer again was 2, and now let's say I tried to go w greater than 3. So here's the problem. Notice it gives you these gigantic, to the 52nd and negative 52nd. Those are obviously wrong. So that tells, if you try to go one direction, either, and it gives you this gigantic positive number or some gigantic negative number, say like in scientific notation, that tells you that there is no other solution greater than that 2, that you need to instead go the other direction, okay? So if you see these values right here, like for w and for m, that tells you there's no solution greater than 2. You have to go the other direction, to potentially get another, to get another solution, to get much more reasonable answers. Okay, so that's how you could solve that last problem. All right, I hope you enjoyed this video. If you did, please do give it a thumbs up, subscribe to my channel, and sign up for notifications. Again, I tried to pick problems on this video that are fairly difficult and hard to solve by hand. Now, there might be a couple on here where you were able to identify the answer quite easily, or maybe even solve it, by hand easily. And again, as I mentioned earlier, if you can do that, that's great. That means you are ahead of the game. That means you are on track, to earn a great score on your next, official test, whether you're taking it coming up in May, in a couple days, or, sometime in the future. But anyways, I hope this went through and showed you how you can use Desmos to solve some of the hardest questions on the digital SAT math section. If you haven't done so already, please do check out my Ultimate Desmos Guide to Digital SAT Math. I go through all the advanced skills. I go through all the skills that I demonstrated on here, like, regression to intercept form, and solving sum and product of roots problems, and, all kinds of other advanced, operations and skills that you can do with Desmos. Otherwise, good luck in your studying for the digital SAT math section.